welcome back, folks. What I want to focus on today is the alternative definition or model for light that we mentioned in class. So just as a quick review, we want to talk about light. We can discuss light both in terms of the wave model, where we think of light as being a sinusoidal wave propagating through space at the speed of light. The other model that we can employ is the particle model, where we said that we can take all the energy comprised in that wave of light and focus it down into a tiny, tiny little particle that again can propagate through space and collide with something in a classical sort of sense to transfer that energy to the other object. All right? So when we refer to a particle of light, recall that we call that a photon. So a photon is the definition or the word we use for a particle of light. Now the reason why we like to use photons when we talk about light interacting with atoms is because the photon model is just a better model to use for explaining how light interacts with really tiny things like atoms. Now, just to give you sort of a pictorial of what I'm talking about here, let's say that this little circle here represents an atom. And my sine wave here, my propagating wave, represents a wave of light. Okay? Now what you're going to notice here is that the wave of light is really large in amplitude and size compared to the atom. So as a result, if this light wave bumps into this atom, very little energy from the light is going to be able to be absorbed by that atom because we cannot concentrate the energy in the wave. Think of it this way. If I'm talking about a wave at the beach, and you have one particle of sand that wave is interacting with, that particle of sand is only going to feel a very small component of the total energy of that wave, because I can't concentrate all the energy of the wave down into that tiny particle. It just feels a small portion of it. Now, if I'm talking about a photon, where this would be my photon here, banging into an atom, that's more of a collisional sort of thing where all of the energy of the photon can be transferred and focused down on the atom. So from the point of view of light interacting with really tiny particles, a particle-particle kind of interaction is going to be a much more effective transfer of energy. Okay? So that's why we use the photon model when we talk about the interaction of light with atoms, which is ultimately where we need to go. So let's focus again on the photon and see if we can come up with a relationship to discuss its energy. All right? So remember, we kind of talked about the importance of the energy of light and what that sort of relates to. So we talked about how, for example, the energy of the light is directly related to its wavelength or frequency or color. Now, if we want to define a photon energy, we're going to use this equation right here, where big E is the energy of the photon. That's equal to a constant h times nu, which is the frequency of the light. So in a sense, we're still talking about wave-like properties in terms of frequency here, okay? Because our two models are considered to be more or less interchangeable. Now the h, which is the proportionality constant that we use here, is called Planck's constant, all right? And Planck's constant is actually given a value of 6.626 times 10 to the minus 34th joules times seconds. Okay, so it's an energy unit times a time unit. Now, there's something else that we could do here as well. Remember that nu is equal to the speed of light divided by the wavelength. So nu is equal to c divided by lambda. We saw that in class. Now I could do a simple substitution here, where I could take c over lambda and put it into my nu expression here for the energy of the photon. And when I make that substitution, I see that the energy of the photon is equal to Planck's constant times the speed of light divided by the wavelength of the light. So again, I can get an energy relationship for my photon either from a frequency, in this case, or from a wavelength, in this case. All right? So let's see how we might actually use this. So one thing I could do in terms of a simple calculation would be something like the following. I could calculate both the frequency and the energy of a photon of green light. Let's just say green light has a wavelength of 550 nanometers. And that's about the center of green. Okay, so that's going to be the wavelength of a typical photon of green light. So I want to find out how much energy it's got and what frequency it's got. So the first thing that I've got to do to make all the units work out is I got to convert nanometers to meters because, for example, in my speed of light, I'm talking about units of meters per second as we saw in class. So I'm going to go ahead and convert nanometers to meters here. So I know that 1 meter consists of 10 to the 9th nanometers. I can say there are 10 to the 9th nanometers in a single meter. So we see here that nanometers are going to cancel with nanometers. I'm going to be left with meters. And to sig figs, I get 5.5 times 10 to the minus 7th meters. So that's the wavelength of my photon of green light. So now if I want to get a frequency, I can put that number into my frequency equation where nu, or frequency, is the speed of light divided by the wavelength in meters. Okay, so there's my speed of light in meters per second divided by the wavelength in meters. And again, what we see here is that meters will cancel top and bottom. I'm left with inverse seconds. I get a frequency of 5.5 times 10 to the 14th inverse seconds or hertz. All right? So once I have the frequency of the light, I can then go back to my energy equation for the photon and plug that in. So I know that the energy of the photon is Planck's constant h times the frequency of the light. Okay? Planck's constant is 6.626 times 10 to the minus 34th joules times seconds. Going to multiply that by the frequency of the light, 5.5 times 10 to the 14th inverse seconds. We notice here that, of course, seconds are going to cancel top and bottom. I'm going to be left with energy units of joules, and that's what I should get because I'm calculating an energy. So when I do the math there, I get an energy of 3.6 times 10 to the minus 19th joules. And keep in mind, that's the energy per photon of green light at 550 nanometers. Now, why is that important? Because now, if that green light photon collides with an atom, I know exactly what energy is going to be transferred by collision now to that atom, and that in turn is going to tell us something about what the electron in the atom is going to do in response to that event. And that's how we're going to probe the position and activity of the electron in the atom. So what we're going to do next in class is we're going to talk about a simple model to examine exactly that situation. All right, so that's good for now, and we will see you next time.